Alrighty, good afternoon, everyone. Welcome to our to SI webinar on powering AI, the semiconductor ecosystem at the foundation of data centers. I see we have some folks trickling in here, but we're going to go ahead and get started right at the top of the hour because we've got a lot to get through in the next 60 minutes here. My name is Eric Hadland. I'm the Director of Technology Policy at the Semiconductor Industry Association. Work on our R&D portfolio as well as some reports like this one that we release periodically throughout the year. In case you did not see, SIA released a report on this topic just yesterday, which contains a lot of information about the variety of chips that go into enabling data center AI capability. And we're going to spend some time over the next hour talking about that. And the report also contains some market predictions to give you a sense for just how much opportunity there really is in this space. A quick caveat that everything we talk about today is going to be focused on data centers, and there is another side of AI for AI at the edge, and that is something that we will seek to address in a different work product. But for today, we're focusing on data centers. The report that we're going to discuss was written in partnership with Deloitte, and we are honored to have Duncan Stewart here with us today, who's representing Deloitte. Want to thank them for all of their expertise and contributions that went into this report. And certainly you're going to see that there was a lot of work from them to enable all of this. Duncan is the Director of Research at Deloitte and is one of the co-authors of their market predictions every year for telecommunications technology. And Duncan, help me out with the last part of this.
Media and entertainment.
Thank you very much. Duncan's going to rip through about a 15-minute presentation, and then we have the opportunity to hear from a selection of speakers from our companies about the role that each of their companies plays in this AI data center space. So Duncan, over to you, and floor is yours.
Thank you, Eric, and thank you very much for the promotion. I'm actually Director of Research for Deloitte Canada across TMT, but the global thing is nice. I appreciate that. I'll make that formal later. I'm also, though, the Managing Director of Deloitte for our semiconductor research, both in the United States and globally. And that's really why I'm here today. As part of that, I'm getting pulled into a lot of conversations around data centers. So if I could have the next slide, please. This is something that I think probably nobody on the call will believe, but I swear to you is still true. I can still go into meetings and I'll say, hey, you know all those AI data centers? They're built on chips. And people will go, you mean potato chips? And I swear in 2026, it is still necessary to tell people, no, the foundation of the modern world economy in general, technology for sure, and certainly data centers is built on chips, not one chip, hundreds, thousands, tens of thousands, millions of chips, billions of dollars, maybe even that magic T word, $1 trillion. So all of that applications and models and algorithms and data, they all sit on top of hardware, very specifically semiconductors. Next slide, please. Now, one of the things that people sort of tend to aggregate is they're fairly good at understanding here is a specific AI chip, and then here is a data center that fills something the size of Manhattan. In between, lay people generally get confused. The basic unit of compute inside a data center is what we call a server rack. And the way I like putting this is a server rack is approximately the size of your fridge. It's about 6-ish feet high, about 3-ish feet wide, and about 3-ish feet deep. 2 by 1 by 1 meters for those of you thinking in metric. So what we thought we'd do is we tear down one of those data centers, tear down those server racks, come up with a bill of materials, talk about the chips, talk about value content, a little bit about where those chips are made, and also do some sizing of what that annual market might look like. And then I'm going to let my friends from SIA take us home by commenting on future research priorities. Next slide, please. All right, so there's my refrigerator-sized rack, and thank you to the folks, by the way, if any of them are listening at Deloitte, who helped design these graphics. I think these are actually some of the nicer-looking AI data center graphics I've seen in years. So what you've got inside your basic server rack there is you've got a whole bunch of networking stuff, you've got some power stuff, whole lot of compute and accelerator interconnect. more compute underneath, power, more power. All of this stuff together sits in this thing that's, roughly as high as Duncan. Now, when we pull it out, each of these racks contains trays. These trays might be roughly this high. They might be roughly this high. Inside those, what you're going to end up getting is a bunch of different chips, unsurprisingly, on those. Some of those are memory. More of those are memory. By the way, you're going to be hearing the word memory a few more times from me in the next few minutes. But you've also got storage and interface controllers. You've got AI accelerators, which a lot of people call GPUs because they are historically based on that old graphics processing architecture, but we call them AI accelerators. You've got some power and analog semiconductors, and then the CPUs. Now, depending on which tray you are, sometimes there's more CPUs or fewer, more of the accelerators or fewer, but at a high level, this is a good overview. Next slide, please. Top level findings. I already kind of said this, but AI depends on a wide variety of chips. I'll drill down in about 4 minutes into that variety, but each server rack contains more than 4,500 different chips. Some of them are fairly big, like, kind of postage stamp size. Eric, I just dated myself. Nobody else on the call knows what a postage stamp is, but as the old guy on the call, about the size of a postage stamp. Some of those chips are tiny. They're kind of almost barely larger than a pinhead. A leading AI data center can contain up to 45 million of these chips, and actually, there are probably data centers one day that will have even more than that. Incredibly, semiconductors account for 95% of the value. Yes, there is steel. Yes, there is copper. Yes, there are fiber optic things. But overall, semiconductors are essentially almost the entire stack. And within a data center, this gets really important. I'll be coming back to this later. When you hear a number that somebody's spending a billion or 10 billion on data centers, almost 50 to 70% of that has been made up of semiconductors. And that's including all of the concrete and the building and the cooling. All of those other things, as big as they are still much smaller, even in aggregate, than just the semiconductors alone. At the end of the day, building a data center is about chips. Next slide, please. All right. Now, I want to very, very briefly walk you through a few things I've said. I've already talked about racks. I've already talked about trays. Then you've got printed circuit boards. On those boards, you've got a chip, which is a package. And then within those, and this is quite cool, what we're starting to do is we're starting to combine dies into a thing called sometimes a chiplet. Always one of them. I can't go without a webinar without saying the word chiplet. I always enjoy saying that. But you can have these dies actually combined with other dies inside the same chip package. That's a really hot new trend and very much a big part of the success of AI chips. Next slide, please. Now, I'm not going to drill down on this one. This gives you the whole semiconductor stack. For those of you wondering if you need to go out and get laser eye surgery, I find this is a fairly good place to start. But as you can see, we've got logic there. That's largely CPUs and AI accelerators, but increasingly things like ASICs and FPGAs. Don't forget the networking. Networking is a very, very large business. In that purple column, a whole stack there of memory. As I said, I'm going to be talking more about memory in a second. You've got analog, and that gets fairly complex, but all kinds of stuff in there, converters, power management, all that kind of stuff. And then you've got actually some interesting discrete devices, including things like optoelectronics, sensors, transducers. Keep an eye on that optoelectronic space. That one's poised to get really hot in the next year or two. Next slide, please. Okay, now here comes the disclaimers. I was really happy with my colleagues from Deloitte to work with the great folks at SIA, and we put together kind of this chart. You can see these are all estimates. Nobody actually breaks out an exact number. We had to kind of, sharpen our pencils and try figuring this out. Ballpark, the semiconductors found inside data centers in 2025 were roughly $320 billion, plus or minus a bit. We have predicted that in 2026, that number will more than double to $670 billion. We then have the two lines you can see here. Green line is our optimistic scenario. Orange line is the more conservative 15% growth. Now, here comes the fun part. This is why my job is so fun and Eric's job is so fun. 4 weeks ago, all of the hyperscalers started revising the numbers for their CapEx that they were going to spend for the year on data centers that they had already revised in January and February. So roughly every sort of 2, 3 months, they seem to be taking the numbers up. And I want to slow down here because two things are going on. First of all, the hyperscalers are buying more chips, greater number of chips. They are building more servers, more data centers, more gigawatts, more accelerator equivalents. So the that is a big trend, and they are increasing that in response to what they perceive a need for more AI processing sooner rather than later. Okay, so even in April, May, they were saying, I'm building more AI capacity. However, the other thing that's going on is that the semiconductors inside, specifically the memory chips, are costing more than they thought they would 3 months or 6 months ago. So there are two tailwinds right now. At the same time, the companies that make the trays and the servers and the racks that go inside these data centers just finished reporting last night, and all of them are saying our AI sales are growing even faster than we are expecting. One of these companies that makes these server racks reported that their AI revenues grew 760% year over year. So there's this tremendous confirmatory data point out there. The final thing that happened is this morning, our friends at WSTS, which is the World Semiconductor Trade Statistics Association or organization or something, they're my go-to source for global semi sales. They came out this morning and they said, hey, you know what? We used to think that total chip sales, not AI, total chip sales this year would be about roughly $975 billion. And then this morning they said, oops, we were close. Actually, it's going to be $1.5 trillion. I remember 2 years ago thinking the industry was going to struggle to get to a trillion, but total chip sales will be about 1.5 trillion. And it looks like our numbers here are very much on the conservative end. Even only AI data centers alone, we kind of think that all of these numbers are, I want you to take them as a minimum. The numbers are almost certainly going to be even higher than this, but that slope is directionally correct. We are looking at over time approaching and then passing $1 trillion in AI chip. I was joking with Eric before we started this call. I wish we had an ability to make a blue line, which was our hyper optimistic growth curve, because that would be probably a better picture. But all in, I want you to kind of have a sense that this 320, 670 is probably going to be beaten by a lot. 905 will probably get beaten by a bit. 1.2, we will see. Next slide, please. Super important. Of the value, most of the value is found in those AI accelerators, which is a combination of logic and memory. But don't forget the CPUs, don't forget the volatile memory, don't forget the connectors. You can see that scattered across all of this, all of these are essential. You can't build a data center without all of these, even though 3/4 of the value is found in those AI accelerators. Don't neglect the rest of the pie. They are equally mission critical to building these AI data centers. Next slide, please. The really important. There are semiconductor plants out there that are a year or 2 or 3 old. Those are advanced node plants. There are semiconductor plants where they are making current generation nodes, 10 nanometer to 28 nanometer. That includes a lot of the memory plants. And then you've got the more foundational mature nodes. Certainly, at the compute tray level, there's a concentration on those advanced nodes. But when you look through interconnect, IPMI, power, CDU, all of a sudden you can see I need cutting edge plants, medium edge plants, and trailing edge plants. They are all critical for this AI ecosystem. Next slide, please. And That's my 15 minutes. Eric, I think I was 16 seconds over there. I hope you don't penalize me too much. But that's it from me. I'll be hanging around for a bit, but over to Eric for some of the implications.
Sounds great. Thanks very much, Duncan. And for those of you who are wondering, we go into this information and a lot more in the report that you can find on our website, semiconductors.org. Um, so, SIA occasionally runs studies like this to help us make a really informed fact base that we can use to define some priorities for government, to help support and accelerate our industry and ensure AI leadership and semiconductor leadership domestically here in the US. So we will be using the findings of this report to describe some mechanisms for strengthening domestic chip production, working on securing our supply chain, both domestically and with friends and partners around the world, adopting a suite of economic interventions that can help us to support different segments of the ecosystem, because as Duncan stated, all of these different chips are critical to ensuring AI leadership, and they need different things. So we're going to do some thinking on that. Additionally, this technology space continues to evolve very rapidly, and there are R&D investments being made, new businesses being started, and we want to make sure that we can help our friends in government understand the best ways to invest in those next technologies and businesses to ensure that the US always has the best technology. None of this is possible without a robust workforce, but we need to make sure that they are trained for the skill sets that are going to help us produce these technologies and bring them to scale. And finally, there are regulatory environments that are rapidly expanding as well. And we want to make sure that those regulators are dealing with the very best information and they know what companies need to be successful. So with that, we are going to turn to the portion of our event where we hear from some of our companies. And we're going to start with Baha Fahim from Intel, where he is a senior fellow. And without further ado, Baha, I'll turn it over to you.
Thank you, Eric. Um, Pleasure to be here to talk to you about advanced logic and the role that we have within Intel. I'm from the data center group specifically, and we'll go through some material around how AI is evolving and Intel's role into that. So we can go to the next slide. In general, there's a number of key functions that, our compute infrastructure plays in. I'll outline a few of them, and then we'll outline some of the products and some of the evolving trends in the technology space. First is that for specifically from an AI perspective, there is a training function. Think of training, model training as in, training large models based on large amounts of data. And it's lots of massive parallel computation that is done predominantly based on GPUs, accelerators, and so on. And that is one of the key functions that is part of the AI compute scale. Then there's inference, and inference is kind of really it's real time. You're kind of extract using the trained model to determine to execute fast predictions, fast results, determine fast results based on that. And it's all done in real time. Needs to be done in the data center space that's done by millions of users concurrently. And then there is system orchestration, whereas a lot of CPUs need to coordinate a lot of data movement between compute, memory, I/O. A lot of other data movement happens between a lot of the devices within the data center. And the data movement and system orchestration is super critical for keeping the AI machine running efficiently. And then there is the scale. It's not just within the compute rack itself, but it's also across connecting the various CPUs, GPUs, and other accelerators together. And there is dedicated, there's networking and interconnect problem that is required to be solved in order to allow AI to scale appropriately. So moving on to the next slide. So from an Intel perspective, really there is four key swim lanes that we're really focused on primarily. One of them is on the general purpose CPU. On the data center side, we call that the Xeon architecture or the Xeon segments. These are products that Intel has been making for decades in the data center space. very complex products for both the hyperscaler, ranging from the hyperscaler targeted products to the enterprise and OEM space. Those are built based on tens, hundreds of x86 cores with a lot of requirements from a data center perspective, whether it is memory RAS, whether it's I/O, whether it is security requirements, all bundled into the CPU development there. And there's a whole number of different products targeted for specific usage models. And then there is an evolution from the general purpose CPUs, a custom CPU. And the custom CPU, Xeon CPU, is really optimized for AI head node. There's developments there which is optimized for an AI head node, basically improves memory capacity, which is crucial for AI, improves memory bandwidth, and also enables optimized edge processing units, EPUs, which are really for networking and at the edge. And then there is GPUs. These are your general, historically, they're graphics focused, but they're really AI accelerators for the most part. They're really good at massive computation, and rack scale inference accelerators for data centers is kind of the one of the key focus areas that we focus on developing. And then there is NPUs, which are neural processing units. These are specific types of AI accelerators. They can offload a lot of tasks from both the GPU and the CPU. And they're focused on a lot of those machine learning tasks that can be done more efficiently on an NPU than either of those. So a number of different silicon products and targeted for specific usages, they all interact together to provide the best possible AI machine solution. Now, all of the Intel products that are used in Intel Mix, focused on all of these, does them on both an Intel x86 architecture, which is historical architecture that Intel has been developing for a long time, and done in Intel Foundry or Intel manufacturing facilities, mostly focused in the US and a few other areas. Okay, so we can go to the next slide. So in order to deliver a lot of what we just covered in the previous slides, there is a whole bunch of different areas that we're really focused on making sure that we can sustain. One of them is, a lot of these products are built based on key ingredients. Those ingredients are called IPs, whether it is the core, which is the fundamental computing block, whether it is caches, whether it's memory, whether it's I/O, and a whole product architecture that actually integrates all of those dies, chiplets together, assembles them to meet the demands of each one of these product segments. And a whole architecture roadmap and strategy to meet these needs is fundamentally critical to make sure it's all balanced. In essence, you can't have, for the best possible compute and best possible memory, you need to have the interconnect and the fabric that connects them together. And you need to have a power efficient total solution that can actually scale for the performance needs for all of them. Second vector, which is crucial in the space, is the process technology. This is effectively the blueprint for how we actually make the silicon products that we do, which fundamentally relies on a whole plethora of different process nodes, but it requires a certain amount of advanced process nodes. Currently, Intel is focused on this 1.8 nanometer, which is 18A, and the upcoming 1.4 nanometer, which is we codename 14A, and nodes beyond that. Those are more advanced nodes, but there is also a wide range of other process nodes that are more mature nodes, lower cost, more scalable nodes as well. And then the critical, we've kind of made this evolution for a while now, and a lot of our data center products are complex enough. They assemble tens and hundreds of the cores, lots of memory channels, lots of I/O lanes, and the complexity of the product itself makes it such that we build the products based on multiple dies, multiple chiplets assembled together. Now, how is that done? There is lots of assembly technologies that enable that, from 2D, 2.5D, and 3D, where two dies are physically stacked on top of each other to enable a smaller form factor within what we need for our platforms. And those are technologies that really we invest a lot in, and they're crucial for AI in the future. And then there's packaging technologies where we can also integrate a lot of the interconnects between a lot of those dies together, complex products together, and packaging technologies that supports that. And then there's various interconnects that are targeted on a lot of these data center products. One which is predominant and very common in the industry is PCI Express. And PCI Express is a high-speed interface that's used to connect a whole number of accelerators, but it's also a whole bunch of other devices as well. CXL, and we have multiple coherent interfaces between sockets. A lot of our systems are designed such that we can build not just one CPU socket, but or more than one of them all connected together seamlessly. And optical links that allow us to connect those products together in faster and more efficient manner than what we've historically been able to do. And then more importantly is not just the silicon itself, but a platform that can enable that, and comes along with power delivery, that comes across with concepts such as how we provide our infrastructure around the products themselves, as they're fundamentally crucial to delivering those solutions as well. Okay, so that's kind of what I had.
Thank you very much, Baha. Really appreciate you describing the role of some of the advanced logic components that go into the server racks. Next, we're going to be hearing from Athar Zaidi from Infineon. I know many of you will have heard about the significant power requirements for AI, and Zaidi is going to talk to us a little bit about that. But representing Infineon, Athar, over to you.
Thank you, Eric. So we talk about compute. Compute is on the advanced nodes. Power is on the mature nodes. And I will walk you through of what role does power play in compute. So if you look at Infineon portfolio, next slide, please. We have a very extensive portfolio of power and grid to core. So we take medium voltage grid voltage, 35 kilovolt AC, and we convert that 35,000 volts all the way to less than 1 volt when it hit the processor. And there are multiple stages that happens in between. Infineon has portfolio from energy generations to energy transfer to energy conversion, and we call it grid to core. And it is not only silicon, it's silicon carbide and gallium nitride. Next slide. So as I mentioned, high voltage AC gets converted into sub 1 volt when it hit the processor, and it goes through the various conversion stages. And every conversion stage, you lose some efficiency. And today's the data centers are running at 85% efficiency if you aggregate all the conversion stages that happened in the power path. But we are trying to shape the industry by coming with new topologies, whether it is on the power supply or solid state transformers or battery backup units or intermediate bus converters. And the goal is to gain some of these losses back, because these losses are manifested in the data center as heat, and it's a double whammy because it adds to the TCO of the data center provider, and also the inefficiency in the system manifested itself as heat, and you have to take the heat out from the system, which also costs money, and it affects the reliability of the system. So the goal is to squeeze as much as possible in every stage so that you improve the efficiency at the system level. Next slide. And how are we doing it? There are various ways of delivering power to the accelerators. Accelerator is where all the magic happens. That is the most power consuming component in the data center rack. Everything pretty much, I would say 80-85% of power which is being delivered to these accelerators is what we call the lateral power delivery. The power is built around the processor. And it was okay when the processor voltage is a processor power used to be less than 1 kilowatt, and the peak currents used to be less than 1,000 amps. But now we are seeing that these accelerators are approaching average power of 2 kilowatt, and there is a clear roadmap of many players, including hyperscalers, to go to even 4 kilowatt. and the peak currents are moving from 1,000 amps to 10,000 amps. And power is equal to voltage times current. Higher the power, higher the current, but the losses are the squared of current. So every millimeter that current has to travel, and those parts are lossy. You cannot have 100% lossless system. So the loss in the system, they grow with the squared of current. So that's one effect what is happening. The second effect what is happening is the core node voltages are coming down. So it used to be 1 volt, and now it is already at 0.7 volt, and there is a clear path to be even less than half a volt. So for the same power, when the voltage comes down, the current needs to go up, and the squared of current manifests itself as losses. So one way to solve this problem is to bring the power as close to the processor as possible. And industry is working on what we call the backside lateral and vertical power delivery, which is hybrid case, in which some of the power is on the backside, some of the power is still on the lateral side. But eventually, the goal is to bring all the power to the processor underneath the processor itself to minimize the travel, and eventually even cross the boundary of the motherboard, which is shown as the last drawing, what we call the SIVR, substrate integrated vertical power delivery systems. And this is where the power will get completely married to the compute. Right now, power is still after the fact. When a $1 billion investment is made on next generation XPU, power guys like us or TI are not at the table at the same time. But because the belief is that power guys will find a way to solve that problem, but power is becoming the bottleneck at this point of time. And we believe that we are shaping the industry, that we make this marriage so close that the divorce is super expensive. That's the idea, to bring the power close into the substrate of the processor itself. Next slide. So how are we doing all of this? Fabless companies, especially in case of power, have an uphill battle. Why? Because wide bandgap, silicon carbide, gallium nitride is pretty much everything is done by IDMs. Even in trench MOSFETs, Infineon has the thinnest trench MOSFETs in the world, which are approaching 20 micron in silicon thickness, and we do it in our world's largest 300 millimeter fabs. In Germany as well as in Austria, and the demand on powering AI is very lumpy. There is no intelligence in forecasting AI growth, and we have seen from nowhere the demand comes, and unless you have a destiny in your own hand by having your own fabs, it'll be very difficult to support that demand. And we have been on this journey now for a while, and now we are controlling the destiny. Our own destiny. The other thing that I want to point out, that these racks, there are a lot of components on these racks. There are thousands of chips, but there are roughly 600,000 components in Grace Blackwell 72 GPU configuration. So PPM level on power chips don't work, because if you aggregate all the PPMs, it turns out to be a percentage at the data center level, and these racks are super expensive. So we are shaping the industry to think about parts per billion, not parts per million, because it is eventually the PPM at the level at rack level than the component level. And companies who have a lot of experience working in the field of automotive are best positioned to address these market needs. And one of the ways to do this is to manufacture what we sell. All right, next slide. So ultimately, it all boils down to energy efficiency. We are improving the efficiency of the system by 8 to 10%. We are increasing the power density, and eventually minimizing the equivalent CO2. And robustness and reliability is the key in everything we do. I think that's it from my side, Eric.
All right, thank you so much, Athar. I really appreciate you taking us through all of that. Next up, we have Tom Barber from Global Foundries, where Tom works as the Vice President of Communications for Infrastructure and Data Center. Also, for my remaining presenters, we're running just a couple of minutes behind. You will have my eternal gratitude if you can help us find a minute or two back. But Tom, over to you to talk to us about data center optical networking.
Thank you, Eric. So yes, I'm responsible for the data center business within Global Foundries, inclusive of silicon photonics and power and a whole bunch of other fun stuff we do. But today the focus is really on silicon photonics and optical networking. Go to the next slide. So it's interesting when we switched from a traditional data center to an AI data center, we talk about the compute a lot, but the model of data movement in the data center changed dramatically as well. In a traditional data center, you were really focused on data retrieval, right? The model was Netflix. Can I stream a movie, efficiently without any interruptions? When we go to an AI data center, it's really about movement within the data center. You have these very large, billion, trillion parameter models that need to be used iteratively, right? So you need to use the data and you need to use the parameters all repeatedly. And so you need to use them across hundreds or thousands or even a million GPUs. And so it's a very, very big data movement problem within the data center instead of moving data in and out of the data center. Next slide. So how do we do that? It's really broken up into three distinct networks that have different responsibilities. At the base, you have a scale-up network, which is your bottom level, which is connecting, today 72 GPUs in a rack or 144 GPUs in a rack, depending on how you do your math. But that needs to scale out to, hundreds or even a few thousand GPUs across multiple racks. When it does, you go from, spanning a couple of meters to spanning tens to hundreds of meters. And that's really where you see a transition in that network from copper to optical. The scale out network, that's where you take those clusters of hundreds or thousands of GPUs and you build, an entire data center or an entire data center campus of, hundreds of thousands of GPUs. In that case, you're typically spanning, hundreds to maybe a couple thousand meters, but your data rate goes down by about a factor of 10, right? So it's not quite as much data movement between the clusters, and that is where sort of the traditional optical communication is today. And then to get to a million GPUs, you really can't fit that under one roof unless you're going to take up the entire borough of Manhattan. So that's where you have data center campuses linked together. The data rate per GPU is a little bit less there, again, by about a factor of 10. But that's where you get the long range optical links. So you're talking about coherent communications with much more sophisticated optics. Next slide. So why do we go to optical networking? Number one is reach. Again, if you look at the evolution of a rack from NVIDIA, they went from the networking being at the top of the rack to moving it to the middle of the rack when we went to 200 gigabits per second. Why? Because you can't make copper go more than a meter at 200 gigabits per second. When you go to 400 gigabits per second, it gets cut in half again. So you're talking about half a meter. So if you really want to go any kind of distance, and particularly if you want to span multiple racks, you have to go to optical at these speeds. So that's number one. Number two is the density. Again, you're pushing as hard as you can to get, a single twisted pair to support 200 gigabits per second. 200 gigabits per second is kind of minimum for fiber, right? And if you go to the theoretical maximum, you could do almost 20 terabits per second over a fiber if you used, a number of wavelengths. So there's almost unlimited bandwidth per fiber, which allows us to scale the bandwidth density tremendously. The next bit is energy efficiency. This is where there's a lot of debate. If you look at traditional pluggable optical transceivers today, they're probably 25 picojoules per bit. But there's a lot of that overhead we can get rid of by moving the optics closer to the SoC or the switch. The number one thing is the DSP, which is about half the power consumption. You can get rid of the DSP just by moving it closer to the CPU because the DSP's main function is actually to correct for errors in the transmission of the signals from the SoC to the pluggable over the electrical wires. It doesn't actually do that much on the optical side. The second thing you do by bringing it closer is you reduce the power of the SerDes, right? So of that 25 picojoules, almost half of it is SerDes. So if you bring that really, really close to the CPU, you can bring that SerDes power down to less than a picojoule per bit, which allows you to get to less than 5 picojoules per bit overall. The last thing is, we talk about the power consumption of these GPUs, that's assuming 100% utilization. And there's cases today where due to stalls waiting for data, that utilization may be only 15%. And the goal is to really move that utilization as high as possible by making sure that the data that's needed for the next computation is always there. And the way we do that is by having, virtually unlimited bandwidth using optical networking. Next slide. Just briefly, I'll go through this. So we're seeing an evolution from traditional OSFP to XPO on the edge using retimed DSPs. That allows us to get a little more density on the faceplate. But the real transition is happening when we go to linear pluggable optics. That's again where we get rid of the DSP and we can reduce the power consumption by about half. That does require significantly higher performance optics. We need about 30 to 40% more bandwidth in the optics to take care of the fact that we don't have a DSP. We also need to be much more linear to make sure that we don't have any errors. The last stage, as I said, is moving those optics as close as possible to the processor. Near packaged optics is when it's on the same PCB, but we're really shooting for co-packaged optics where we take those optics and we put it either on the same substrate or even the same interposer as the GPU or the switch. Next. So what does our solution look like for this? So it's something we call Scale, which is Silicon Photonics co-packaged advanced light engine. It is a known good optical engine chiplet that is able to be integrated on either the interposer or the substrate, depending on your preference, with your XPU. That optical engine includes everything you need to do your optical networking, including the electronic IC to take the die-to-die electrical interconnect and drive the photonic IC. It includes all the modulators and the receiver you need to transmit and receive the optical signals. It's got a detachable fiber connect, which allows you to do easy assembly of your servers using a common plug and fiber interface. And it's all packaged up, tested, and delivered as a known good chiplet that effectively replaces the I/O chiplets that are on the GPU today. There's a new industry standard that was launched by AMD, Broadcom, NVIDIA, Meta, Microsoft, and OpenAI. So a lot of good names called OCI, Open Compute Interface. And the solution we have is compatible with that interface today. It's actually extendable. The platform we have today, we believe will support up through Gen 3, which will give you 4 times the data rate of the initial Gen 1 launch. And this is going into production beginning in 2027. And that's what I have.
Excellent. Thanks very much, Thomas. Appreciate those comments. We're going to turn now to Robert Taylor at Texas Instruments to talk to us a little bit more about some foundational chips. Robert, take it away.
Yeah, thanks, Eric. So first, I want to thank Arthur because none of this works without power. So we need to make sure that as amazing things that all these XPU vendors are making, none of it is going to work without power. So hopefully everybody keeps that in mind. You can go to the next slide, please. So at Texas Instruments, we're doing a lot of great things in power as well, going from 35 kV like what Arthur was talking about, all the way down to the core voltage as well, and everything in between. So whether it's solid state transformers or cooling systems, all these different types of things are happening within our architecture, and it takes lots of different things, not only from power, but also from signal chain, embedded processing. All of these different types of chips are required in order to make these GPUs and CPUs work that enable us to do all the cool stuff that we want to do with AI. Next slide, please. So all the different types of things that are happening, whether it's 3-phase uninterruptible power supplies, alternate energy sources, could be battery management, GaN modules, gate drivers, digital isolators, all of these things that the normal person doesn't really think about. Everybody thinks about NVIDIA or a CPU or a GPU. But again, we need all of these different foundational chips in order to be able to power those, in order to be able to transmit the signals, in order to be able to have those chips function and do what we need them to do. So at TI, we're investing not only in the IP to develop these different types of solutions, but also investing in capacity to support our customers. So we have $60 billion that we invested to help continue to develop new solutions for data centers. In addition, we have lots of other IP that we are developing. So a lot of people think, okay, the latest and greatest IP and development only happens at those advanced nodes, at the 1.4 nanometer nodes. But we have lots of different innovations that we are doing, even at very, as we call them, mature nodes. Mature nodes, whether it's in power, whether it's in signal chain, even in some of our embedded processing, there's a lot of technology advancements that are happening that are necessary in order to be able to make sure that they can get the most out of these advanced chips that we're trying to process. Okay, go to the next slide, please. So again, just to reiterate, and Eric, I'm going to try and get you back on time here a little bit. We're investing in capacity, so over $60 billion to meet the growing demand of the AI data centers. So we develop not only the analog, including power and signal chain, but embedded processing also. And the big focus is on internal manufacturing. So we're building these new fabs, whether it's in Sherman, Texas, or in Lehi, Utah. We are working on these new manufacturing facilities in order to be able to provide not only geopolitical diverse sources, but also so that we're able to control the supply as well. So we have not only the wide IP and portfolio to be able to support the data centers, but we also have the sourcing, the manufacturing, and the sales and support to be able to deliver what we need to our customers. Okay, I think that's all I got.
Thank you very much, Robert. Very much appreciate it. Next, we're going to be hearing from Satyadal Bhattacharjee from ARM, who's going to be talking to us about some of their offerings. So, Satyadal, please take it away.
Thank you, Eric. Yeah, I'm going to talk about what is happening with all the agents picking up and the pressure that's putting on the infrastructure, and what ARM is doing about it. So let's get to the next slide, please. So as we all know, our first interaction with AI was through chatbot until OpenClaw came along. And we saw the tremendous acceptance of OpenClaw in no time. Within 5 months, there was like 355,000 GitHub stars and millions of users using them. And as a result, there's tremendous pressure that started happening on the infrastructure side, right? So let's go to the next slide. Agentic AI is more than just automation anymore. It basically represents a massive shift from having passive tools, which runs in the background, to basically a tremendous amount of autonomy, where the agents can now go off and take actions on behalf of the users. And essentially, what it does is basically it gives the flexibility for people to go off and do much more work than they were able to do. And according to Gartner's, by 2028, every enterprise will have some kind of agents deployed in thousands in numbers. And that basically brings a tremendous amount of challenge on the infrastructure side. So let's look at that. So please go to the next slide. So usually when human beings query, it's basically there is a certain amount of time that lapses when you ask a question or prompt and then you get a response back. But on the other hand, when agents are doing that same thing, there is a term that is being coined now called agent swarm, where multiple agents are running and they run much faster than human response time, and they run 24/7. So what it does is it puts a lot of pressure. And you can see here the expected agent queries is supposed to be 15x more requests than human beings. And that basically needs a fundamental change in how we think about the foundation of the data center infrastructure. So we go to the next slide. Traditional data centers were designed for predictable human-driven workloads, web requests, database queries, and batch processing. The AI servers today are typically acting as a head node and orchestrating traffic between the network and the accelerator. And it's mostly doing a prefetching of data and scheduling jobs and so on. But with agentic AI coming in, it's more around a persistent goal-oriented process that runs continuously, collaborates with other agents, and dynamically allocates resources. So this basically means that there's massive amounts of agent workloads that will swarm the current CPUs that are being deployed. And that basically drives a need for a more flexible, scalable, and low latency infrastructure. Next slide, please. So not only the CPU now just does the orchestration work, but it also does work on behalf of the user. And that's what basically includes what we call as tool calling and taking action, which is booking things on your behalf or calling a Uber ride, for example, booking flights and so on. So these agents are running continuously and making decisions on our behalf. And that basically needs a more intelligent, AI infrastructure underneath. So let's look at what ARM is doing about it. So next slide, please. So in order to serve this, focus need of a new CPU architecture for agentic AI workloads, we decided at ARM, to go and address and take that challenge head on. And we have introduced our first silicon called ARM AGI CPU. And as you guys probably know, we have been working very closely with the hyperscalers to build their CPUs, but this AGI CPU is from ARM. And the idea here is to provide an efficient, scalable compute that is extremely power efficient, but it's also built on well-known, proven ARM architecture, which is the Neoverse architecture. So what the AGI CPU provides is, it's a general purpose CPU, but it provides the backbone for agentic systems, which has tremendous demand on making sure that they can coordinate, reason, and manage complex workflows between the CPU and the accelerator. So what we have done is we have leveraged our proven IP. So inside the CPUs, we're using the Neoverse architecture. And within the accelerators, the ARM IPs continues to be used, which is for control plane management and feeding the different cores within the accelerator. So there are two ways in which we are participating here. We have IPs going inside the accelerators, and then we have the CPUs which are connected to the accelerators. Next slide, please. If you look at the ARM AGI CPU, it's built on the Neoverse V3 architecture. It's the same core interconnect and system IP that is there in some of the CPUs that you can find in the hyperscalers. There are 136 cores, and these are all single-threaded cores that can run up to 3.7 gigahertz. They provide, there's around 96 PCI Gen 6 lanes and CXL3 support as well. And there's enough memory to feed these cores. So it's supported 12 DDR5 running at 8,000 plus megahertz. And the memory bandwidth is around 6 gigabytes per second to each of the cores. Essentially, what it provides is enough compute power, and there's a balance with networking and memory to feed these cores. But we do all of this within 300 watt TDP. So we are not a power guzzler, but we are consuming enough power to feed these cores, and it's much more efficient design point. And this power savings can be used to pack more compute within the rack. Next slide, please. On a system side, we have decided to use open systems. So this is what you're seeing here is the Open Rack V3 compatible 1U design with 2 nodes side by side. This is based on the DCMHA standard. And we have contributed the design to Open Compute as well. And the reason why we choose this as our first server is because it enables a new level of dense compute for air-cooled system because it's in 1U form factor. Next slide, please. At a rack level, if you look at the air-cooled rack, at a 36 kilowatt rack, we can pack around 30 1U 2-node servers, which basically equates to more than 8,000 performant cores, and these are all single-threaded cores. And that basically leads to a much dense compute than what the industry has seen in the past. On a liquid cool side, we are able to get a 200 kilowatt rack around, as you can see in the slide, around 42 8-node 1U servers, which yields 45,000 plus cores. And that's basically what we are seeing tremendous demand to have this tool calling and agents running on them in a disaggregated architecture, which is coupled with the decode and pre-full phase. Next slide, please. We are tremendously grateful for a wide set of partners who are collaborating with us. The lead partner for the AGI CPU is Meta, and they are the ones who came and collaborated closely with us to create it. And now we see a host of other companies who are extremely interested in taking AGI CPU, not just for general purpose compute, but also for agentic workloads as it's picking up at a rapid pace. Next slide, please. This is my last slide. As I think most of the audience here is aware, we have come a long way in terms of built a robust ecosystem. These are all built on standards and open ecosystem. So the silicon and server and rack that you saw, which is powering the next wave of AI, is all built on the standard ecosystem with a wider set of partners across chiplet server designs. And you'll see many more servers that will come to the market this year and next year. With that, I will conclude my speech. Thank you so much.
Thank you very much. And we are going to end with our speaker from Cadence, Sherman Ikemoto. And Sherman, I understand you have your own slides, so please go ahead and feel free to pull those up and take it away. We've got just about 5 minutes remaining.
Great. All right. Thank you. Let me make sure I'm able to share.
Yep, we've got your slides.
Okay, great. All right. Yeah, 5 minutes, so I got to go through kind of quickly. Yeah, semiconductors, of course, are the foundation of AI, and the scale of what we're building in the US here for AI is staggering, of course. Thousands of chips in a single rack, trillions in investment, and semiconductors account for 95% of a compute rack's value. But today in this presentation, I'd like to broaden the discussion. The common view is that the chip or the compute rack is the unit of compute. But in recent talks, NVIDIA's Jensen Huang puts it plainly, the data center, or more precisely, the AI factory, is the new compute, a unit of compute. The GPU is still where it all starts, but it's not really where it all ends. So it's clear that we're realizing as a nation that the stakes for getting AI factories right could not be higher. So I put this presentation together looking at what this build out, the AI factory build out, must do for the US. We need to win the global AI race. We need to power a new era of prosperity. And because we are power constrained, we need to use our power generation capacity and our grid to its fullest extent. And every one of these depends on what happens inside the AI factory. So to deliver on these aims, every AI factory must excel at three things. We must get semiconductors online quickly, minimizing the time to first token. We must deliver the lowest cost per token. We must work towards reducing that cost over time. And we must be able to produce the most tokens per gigawatt, the most tokens within our power generation capacity. And today, each of these has room to improve. And this is what we'll be talking about over the next few minutes. So the design processes for AI factories today, they haven't kept up with the semiconductor industry. They're falling behind. So we are projecting to need about 122 gigawatts of AI capacity by 2035. But given current trends, we're likely to have to build 162 gigawatts of capacity to achieve that. This is leaving about 40 gigawatts of capacity sitting idle. And this is an alarming thought. Capacity at this scale has huge implications for our nation's power generation capabilities. And what's behind this potential major waste of capacity? Again, its semiconductor development has way outpaced the development of the tools and techniques for designing AI factories. So in addition to semiconductor design, Jensen at NVIDIA likes to talk about what he calls extreme co-design and simulation of the AI factory. And it's this process that is behind the times today. So he talks about the AI factory as being one of the most complex systems humanity has ever built, billions of dollars on the line. But today it's designed in parts by a vast ecosystem of suppliers with no way to predict or optimize the system before it's built. And I have an illustration here. The F1 cars are built in the same way, but they've solved this problem with extreme co-design processes. So every component of the F1 car is engineered for a single integrated system and simulated in a loop until the whole car is optimized to win. And this is where the AI factory market industry has not adopted the concept at the same level. So I wanted to show you, this is where the concept of an AI factory digital twin comes in. This is an example of an AI factory digital twin. We're walking through a real digital twin that's in operation today. In the upper right, you can see its physical twin. And the idea here is that the digital twin is a virtual replica, not only the way it looks, but also the way it behaves. So you can use the digital twin to understand how your real AI factory is performing, how it's generating tokens, how much energy it requires to generate a certain amount of tokens, and if you're making changes to the AI factory, what will happen in the future to token generation performance and capacity. Like having a digital twin of your own body, you can experiment with it in any way. You can put it on a digital twin of your diet, optimize your diet to the nth degree, maximize the outcome that you're looking for, which might be longevity, or it might be health or cholesterol. All of that can do the equivalent of a digital twin of an AI factory. And I have a quick example. So this is an example of AI factory optimization. We took a digital twin and we ran it through an optimization scenario where we were able to, under the same power envelope, increase the amount of token throughput by 33%. Now, these studies are still early on. There's not a lot of them yet, but we're working, Cadence is working towards being able to put out these optimization techniques for the industry so that the industry as at large can take advantage of this type of throughput and performance improvements. So just to summarize, to deliver on the aims that I stated at the beginning, we must scale up our ability to optimize AI factories for the highest level of performance, tokens per watt, or just in general throughput per total cost of ownership. And if you scale up this problem to the national fleet, we're likely going to be able to turn about 40 gigawatts of stranded capacity into token generation throughput by 2035. So this has a massive, enormous impact on our ability to compete in the global market for AI superiority and also distribute and make available AI capabilities to the masses. So my ask for the semiconductor industry and for all of us that belong to the AI factory ecosystem is to think at the system level, the level of the factory itself, and explore and support the new tools and design standards that will need us to get us to where we want to go. Well, thank you very much.
Thanks very much, Sherman. Appreciate all of that. So for those of you who are still online with us, I hope you found many insights over the course of the presentations about the diversity of semiconductor technologies that sort of all come to bear on driving leadership in AI data centers. To process vast amounts of information, move information around data centers faster and in less energy intensive ways, network a variety of chips together so they function more as single units, and store all of this information until it's actually needed. Again, encourage you to go find the Powering AI report on our website at semiconductors.org. And of course, reach out to us with any questions you might have on that information. Thanks very much for attending, and we'll see you at another SIA webinar sometime soon. Bye-bye.